Yeah, in the previous lecture, we have been considering input output relation for randomly driven linear time invariant systems, and we have shown that for such systems the knowledge of nth order moment of the input is adequate to determine the nth order moment of the response process. That means, if you know the autocovariance of the input, you can find the autocovariance of the output. If you know mean of the input, you can find the mean of the output. We also discussed the notion of stochastic steady state. So, if a linear time invariant system is driven by stationary random excitation, the response can be the response can exist either in a transient state or in a steady state. In the phase in which the response is in the transient state, the response process will be a non-stationary random process, and in the steady state the response becomes a stationary random process. And in transient state, the system response will be affected by the initial conditions, whereas in steady state the initial effect of initial conditions vanish. For the system to enter into a steady state, that means condition to be satisfied for existence of steady state are that the system should be damped and excitation is stationary. If system is undamped, no steady state is possible, and similarly if you apply an excitation which itself is not stationary, there is no possibility of a stationary response. The input output relation in frequency domain related the power spectral density function of the response to the power spectral density function of the input through a transfer function which is a square of the frequency response function. This is valid only in the steady state. We will continue this discussion. Now, we will consider the response of a single degree freedom system to a stationary random excitation. Till now we have considered f of t to be a white noise process. Now, we will consider more general forms of stationary random inputs. We will consider that the system starts from rest and mean of the excitation is 0, and the autocovariance of the excitation process is given by this, where the autocovariance is function of the time difference T2 and T1. We will start with the Duhamel integral representation for the response. Since the system is starting from rest, the Duhamel integral representation provides the complete solution. H of t is the impulse response function, f of t is the excitation. Now, if you take the expectation of the response, so you take expectation on both sides, you get expected value of x of t is expected value of this integral, and that itself is this integral 0 to t h of t minus tau, expected value of f of tau d tau, and since expected value of f of t is 0, it follows that expected value of x of t is 0 in this case. How about autocovariance of the response process? So, you consider the expectation of x of t1 into x of t2. So, this is given by expected value of h of t1 minus tau 1 into f of tau 1, h of t2 minus tau 2 into f of tau 2, d tau 1 d tau 2. So, interchanging the expectation operator with these integrals, we can take the expectation operator inside, and we get the autocovariance of the response to be given by this integral h of t1 minus tau 1, h of t2 minus tau 2, RFF of tau 1 comma tau 2, which is autocovariance of the excitation process d tau 1 d tau 2. Since we have assumed f of t to be stationary, RFF of tau 1 comma tau 2 will be function of RFF of tau 2 minus tau 1. So, I replace this function by RFF of tau 2 minus tau 1. Now, if you recall, the power spectral density function of a random process and the autocovariance function of a random process are related through these equations. So, in terms of a physical power spectral density function, the autocovariance function of a random process f of t can be expressed in this form. Physical power spectral density means the power spectral density function is defined for only positive values of the frequency parameter. The frequency parameter here in this particular derivation, I am using capital omega, because small omega we often use it to represent natural frequency of the system. So, to make that clear, I am using uppercase omega. So, we had this autocovariance of the response to be given in terms of autocovariance of the input through this relation. Now, for this autocovariance of the input, now I use the frequency domain representation and write this RFF of tau 2 minus tau 1 in terms of the power spectral density function of the response process, and that is written here. And next we interchange the order of integration with respect to omega and time, and I will pull out this SFF of omega here, and inside the braces I will have integration with respect to the time. Time appears not only in this h tau 1 tau 2, but also in this cosine of tau 1 minus tau 2 also has tau 1 and tau 2. So, that gets into the braces here. So, we call the term inside this brace as script h of omega comma t1 comma t2. This h can be viewed as a time dependent system transfer function. So, this is given by 0 to t1, 0 to t2, h of t1 minus tau 1 and this particular integral. The question we would be interested in answering is, what is nature of this frequency response function? As time becomes large, that means as t1 tends to infinity and t2 tends to infinity, and t2 minus tau 1 becomes tau, which is finite, what happens to this transfer function? Under these limiting operations, the autocovariance of the input is stationary. I mean, it is always stationary. So, the question would be therefore to consider what would happen to this transfer function as time becomes large and time difference is finite. We have already seen through a direct analysis of response in frequency domain that the power spectral density function of the response is related to the power spectral density function of the input through the frequency response function. Now, the question would be, if we approach this problem through time domain and pass through transients, do we reach the same steady state? Which we should, but it is nice to be able to verify that that indeed happens. Now, the impulse response function is given by this for a damped single degree freedom system. Now, if I now substitute this into this integral for h, this is known function. So, for h of t I will write this function and carry out this integration. If I indeed do that, I get this lengthy expression. This h of omega whole square that appears here is the modulus square of the frequency response function that we have encountered already. This capital omega is a frequency parameter which appears at various places here. Now, clearly this h is a function of both t1 and t2, although at few places the time difference also appears, but if you look at these multipliers, it is function of t1 as well as t2. Now, if I now consider the limit of t1 going to infinity, t2 going to infinity and t2 minus t1 is tau, which is finite, what would happen? Clearly these exponential functions, since they are multiplied by time and time goes to infinity, this goes to 0. So, these terms inside the brace will vanish because I am multiplying by a function, exponentially decaying function, and therefore, these two terms will vanish. Similarly, there is another term here inside this brace, which is multiplied by minus eta omega t1 plus t2. As t1 and t2 becomes large, this function also becomes 0. Therefore, the only term that we will be left with will be this h of omega whole square into this cosine function. Please notice that there is a bracket running across these terms, it begins here and ends here, and the entire term within the bracket is multiplied by h of omega whole square. So, what would remain as t1 tends to infinity and t2 tends to infinity, with t2 minus t1 being tau, is only this term h of omega whole square cos omega tau. So, I get this one. So, therefore, under these limiting operation, the output autocovariance function is given by SF of omega h of omega whole square cos omega tau. Now, seeing that this is nothing but the Fourier transform of Rxx of tau, we can infer that the output power spectral density function is given by h of omega whole square SFF of omega, and this is what we have already derived by using a frequency domain analysis of response in the steady state. So, this agrees, this is nice to be able to verify that. So, we have the output power spectral density function is input PSD multiplied by square of h of omega. So, the steady state variance is given by area under this function and this is given by this. Suppose if we take the case of a white noise, then the output PSD function, if I now substitute into this, I would end up needing to evaluate this particular integral 0 to infinity, and this is a rational function, a polynomial in omega. Evaluation of such integrals can be carried out using Cauchy's residue theorem, using contour integration in complex plane. I leave that as an exercise, and the exercise is to evaluate this integral using the residue theorem and show that this steady state variance is equal to the value that we have already derived using frequency domain analysis. There are few integrals that will be useful in frequency domain analysis of randomly driven systems. I have provided it here. The structure of this integrals are as follows. In the integrand we have ratio of two polynomials in omega, and for different values of n, for example n equal to 1, h1 of omega is b naught by a plus something like a plus omega, and I1 is given by this value. So, for n equal to 2 I get a linear function here and a quadratic function here, and this is the integral, and n equal to 3 I get a quadratic here, a cubic here, and this is the value, and this further results for n equal to 5, 6, 7 etc. are also available in the existing literature. So, one could use such readily available information to carry out the requisite integrations. We have seen that the steady state response variance is given by this integral 0 to infinity h of omega whole square SFF omega d omega. If SFF omega is a white noise process, then it will be a constant and we will be left with evaluation of the integral 0 to infinity h of omega whole square d omega. But if SFF omega is not a white noise, it may be possible to evaluate this integral using an approximation which is explained as shown here. The blue line that you see is the frequency response function of the system, that is this h of omega whole square. If the red line shown here is the power spectral density function of the input, then you could see that the output PSD is clearly product of these two, and in the, if you want the variance of the output, you have to find the area under the curve that is obtained by multiplying these two curves. Most of the area in the product will be contributed by the function lying in this region, where the frequency response function as well as excitation have relatively higher values. So, for purpose of an approximation, in regions where the frequency response function has significant values, we can approximate the power spectral density function as a constant, and we can ignore this variability. So, if I now replace the power spectral density here by its value at omega, capital Omega equal to omega n, and pull it outside, that means you are basically applying a white noise excitation at pitched at this frequency, at this value. If we do that, then the integration of this function can be carried out by integrating only the term involving the frequency response function, and it affords certain simplifications, and we can get a quick estimate of the steady state variance. So, this is an approximation that is often used in practice if you want a quick estimate of the steady state variance. For this approximation to be valid, the power spectral density function of the excitation should not change dramatically in regions where the frequency response function has significant values. So, this assumption for this particular wave graph shown seems to be acceptable, but if you consider this particular case where the blue line is the frequency response function and red line is the power spectral density function of the input, here we cannot make the assumption that the input can be approximated as a white noise with the power spectral density value at the system natural frequency, because when we multiply here over the regions where frequency response function is significant, the power spectral density function of the excitation also changes dramatically. So, the details of this variation need to be allowed for in evaluating the integral, and we will not be able to pull out this outside the integral. If you do that, you will not be getting a reasonable approximation. So, this approximation that is shown here will not clearly work for this particular case. So, when you are using this approximation, if you need to, you have to be sure that you are not making gross errors. Now, we can continue with this discussion and consider now the response of the system to a non-stationary excitation. Here I consider the excitation to be a product of a deterministic envelope and a stationary random process. So, f of t is still stationary, system starts from rest, mean of f of t is 0 and autocovariance of f of t is still a function of time difference, but it is multiplied by an envelope function E of t. It is also called as a modulating function or an envelope function. So, what happens to the response if the system is driven by this type of excitation? Again we start with Duhamel integral. Now, on the right integrand we also have this modulating function, this is deterministic. So, if you take the expected value now, since we are assuming that expectation of f of t is 0, the expected value of f of tau that appears here is 0, therefore, this expected value is also 0. So, the expected value of the response process is 0. How about the autocovariance of the response? So, we multiply x of t1 with x of t2 and take expectation. If you do that, you are multiplying two Duhamel integrals, that becomes a double integral, and the first part of the first integrand is here, this is the second integrand, and if we interchange now the expectation operator with these integrations, the expectation operator enters inside the integrand and we get expectation of f of tau 1 into f of tau 2 in the integrand, and this is replaced by RFF of tau 1 comma tau 2, and since f of t itself is stationary, this becomes tau 2 minus tau 1. So, the autocovariance of the response process is now given by this expression. The new thing is now that we have the terms involving the envelope functions present here. So, now again for the autocovariance of the input, if I now use a frequency domain representation, I will express RFF of tau 2 minus tau 1 in terms of the power spectral density function, and again interchange the integration with respect to frequency and time, I get this expression. And the term inside the brace I will call it as a time varying frequency response function, which is function of capital omega as well as T1 and T2. So, if I write that, that is this. Now, this frequency response function is now a function of the envelope functions. So, that means it carries certain information about the excitation also, it is not just a system property. If this were to be not there, h of t is a system property and cos omega tau is a term that is associated with the Fourier transformation. Therefore, on the right hand side there would be no terms involving the excitation process, but in this particular mode of representing the h, this transfer function is now a property, also contains property of the excitation process. So, one has to be careful in interpreting this as a transfer function. If you are interested in variance, T1 becomes T2 and this h of omega comma T1 comma T2 can be written as h of omega comma t, which is this function. This again a double integral function of envelopes, this is the expression. Now, if I now look at this time dependent transfer function and examine what happens as T1 and T2 become large, you can easily see that the behavior of this function depends on how would these envelopes would behave for large times. If envelope itself goes to 0 as time becomes 0, clearly the transfer function also would go to 0 as time becomes large, and therefore, one immediately concludes that the response would not reach a steady state. A typical envelope function we have already seen for earthquake like loads, it is something like this. This can be of the form e raised to minus alpha t minus e raised to minus beta t, or of the form t e raised to some minus p t with t greater than 0. So, clearly as t tends to infinity, these two functions behave like this. First, of course, there will be some restriction on alpha and beta. If that is satisfied, the function goes to 0 as t tends to infinity, in which case as t tends to infinity, the response variance goes to 0 and x of t would no longer be we would no longer be able to reach any steady state. We will now try to apply what we have learned to problems of random vibration of single degree freedom systems under support motions. These support motions could be due to vibration during earthquakes, or this could also be vibration of vehicles when they travel on rough roads. So, if you consider a simple portal frame, one story, one bay, and if x of t is a support motion, a simple model for this as a single degree freedom system is shown here. Here we assume that slab is infinitely rigid in its own plane, and the stiffness of the system in this direction here depends on stiffness of these two columns. So, this k for example could be 24 EI by L cube, and C represents the damping in the columns, and M is the mass of the slab, and maybe a part of column mass can also be added to this. So, notionally we have now a single degree freedom system in which the support displacement appears here, and Zt of t is the total displacement of the slab. The subscript t here denotes total displacement. So, this is a simple physical model for a portal frame undergoing support motions. Similarly, if a vehicle taxis on a rough road, suppose y of x is the plot of the road roughness, and this MCK system is a model for a simple vehicle which is travelling with a velocity v and acceleration a, and say at t equal to 0 it enters this point and it moves with a velocity v and acceleration a, and we are interested in the displacement of this mass u of t, u as a function of time. If we now set up the equation of motion for this vehicle, we will get this equation. Mu double dot is the inertial force, and the force in the damper is d by dt of u minus y of x, where x is vt plus half a t square. Similarly, k, the force in the spring is k into u minus y of x, where x is vt plus half a t square, with the initial condition u of 0 and u dot of 0 specified. So, we can write this equation as mu double dot plus cu dot plus ku equal to c d by dt of this plus k into y of this. So, this is the force that acts on the single degree freedom system. Clearly, if y of x is a random process, this f of t would also be a random process. There can be additional complexity due to any uncertainties in the vehicle's velocity and acceleration that also would affect this right hand side. Therefore, f of t would be a random process. Okay. So, a structure which is subjected to support displacement where guideway unevenness is a random process is again equivalent to a single degree freedom system with a random excitation on the right hand side. Let us consider this problem of support motions on a portal frame and try to formulate the problem a bit further. So, we start with this model for portal frame. This is a physical model, and based on the free body diagram of the mass here, I can write the equation of motion as shown here. Mzt double dot is the inertial force, and c into zt minus zt dot minus x dot of t is the force in the damper, and k into zt minus x is the force in the spring, and the sum of these forces must be equal to 0, and these are the initial conditions. So, if I divide now both sides by m, I get the equation in the standard form. is zt double dot 2 eta omega n zt dot omega n square zt equal to, now the forcing function is in terms of support displacement and support velocity. Now, I can also write an equation for the relative displacement of this mass m relative to the support. So, if I now introduce a variable z which is zt minus x, I can substitute that into this equation. Zt minus x already appears here and zt dot minus x dot appear here. So, these two terms will simply become cz dot and kz, but this m zt double dot will be m into z double dot plus x double dot, and that mx double dot I take it to the right hand side. So, and this will be now the initial conditions. The initial condition for the relative displacement involves the initial conditions on zt as well as the ground displacement at t equal to 0, the displacement and velocity. So, if I now divide this by m, I get an equation where right hand side contains the ground acceleration. So, if displacement is a random process, clearly the displacement process and velocity when added in this manner also lead to a random process, and if x of t is a random process, x double dot of t would also be a random process. So, in either case we get a single degree freedom system driven by random excitations. Now, we can, if now I model x of t as a stationary random process, can we do a steady state response analysis and find out the power spectral density function, for example, for total displacement? If you want to do that, we start with this equation. On the right hand side, I have 2 eta omega n x dot plus omega n square x, and the solution for zt of t will be a transient part plus this Duhamel's integral h of t minus tau into 2 eta omega n x dot of tau plus omega n square x of tau d tau. In the steady state, we have to find now the PSD of the input. It can be shown to be given by omega n to the power of 4 2 eta omega n omega whole square sxx omega, where sxx of omega in this particular example is the PSD of the support displacement. Therefore, the output power spectral density function is given by this relation. The variance of the total displacement is area under this curve, and that is given by this. So, if you know the power spectral density function of this, you can evaluate this, and if it is for example a Kanai Tajimi and type of power spectral density function, we get in the integrand ratios of polynomials in omega, and we can evaluate it using the list of integrals that I showed earlier, or use Cauchy's residue theorem on this and evaluate the variance. A similar analysis for relative displacement z of t, if we consider, then the equation governing z of t is this, and the solution in terms of initial conditions and Duhamel integral is this. Clearly, the output power spectral density function is h of omega whole square into the power spectral density of the right hand side, which is x double dot of t, and that power spectral density function of x dot of t we have already shown is omega square into power spectral density of x. So, the power spectral density function of x double dot will be omega to the power of 4 into the power spectral density function of the displacement. If you use this, I get the output power spectral density. You integrate this function from 0 to infinity, you get the steady state variance. Now, in studies of long span structures, often the two supports of the system may suffer different support motions. So, a simple archetypal model for that would be a portal frame, where one of the leg is subjected to support displacement x of t, the other leg is subjected to displacement y of t. A model for this would be of this form. It is a single degree freedom system with two supports, and the left hand support receives the displacement x of t, that is due to this, and the right hand support receives displacement y of t, which is due to this. This k by 2 is the stiffness of this column, and we are assuming that the two columns are identical. Therefore, this is k by 2 and k by 2, this c by 2 and c by 2. Now, in this particular case, the notion of a relative displacement is not obvious because the two supports move differently. So, there is no unique definition for a relative displacement, it could be with respect to this support or this support. So, that is not how we will talk about relative displacement in this case. Instead what we do is we consider the total response Zt of t to be made up of two components, namely a pseudodynamic response and a dynamic response. What are these things? To see that, we will let us write the equation of motion. So, if we draw the free body diagram for the mass and write the forces in damper and the springs and the inertial force, we get this equation of motion. This is the force in the left spring, which is left damper, which is C by 2 into Zt dot minus x dot, whereas force in this damper would be Zt dot minus y dot. Similarly, force in this spring would be K by 2 into Zt minus x. For this spring it will be Zt minus y. So, if we do all that, we get this equation, and a rearrangement would lead to this equation, and we define the pseudodynamic response as solution of this system when there is no dynamic action. That means Zt double dot is 0 and we consider only the equilibrium due to the static action, and we define Zps as solution of this equation. We call this as pseudodynamic or pseudostatic response, we have denoted here as Zps. So, this will be x plus y by 2. The dynamic response now we define as Zt of t minus Zps of t. So, this becomes Zt of t minus x plus y by 2. If I now substitute for Zt of t into this equation, and simple rearrangement of terms will give me the equilibrium equation for the dynamic component as shown here. Clearly, this Zt minus x plus y by 2 is here, therefore, this term will be simply z, this is z dot, that will be this, but the acceleration term will contribute to the double derivative of this multiplied by the mass, which appears on the right hand side. Now, we will try to now proceed with this analysis. We will describe the input as follows. If x double dot of t and y double dot of t are 0 means stationary Gaussian random processes with PSD matrix S of omega given by this say Sx of omega is auto power spectral density of x double dot of t. This is, mind you, this power spectral density function is for acceleration in the derivation. Sxy of omega is the cross power spectral density function between x of t, x double dot of t and y double dot of t. Syy of omega is the autocovariance of y double dot of t. These are the definitions for these quantities. Sxy of omega is this limit t tending to infinity 1 by t, xt of omega, yt star of omega, and we already defined the meaning of this is already given in the earlier lectures. Now, if I take conjugation of this, it will be xt star of omega into yt of omega, which is nothing but syx of omega. That means, this is not symmetric function, Sxy star of omega is Syx of omega. Now, if I write the cross power spectral density function in terms of an amplitude and a phase angle, Sxy of omega can be written in this form, phi xy of omega is the phase spectrum, this is the coherence function, and Syx of omega will be the conjugate of this, which would make this minus I sin phi xy of omega as plus I sin phi x of. Suppose for purpose of discussion we take the force in the left spring, that means this spring, whatever force exists in that as a response variable of interest. So, that is k by 2 into Zt of t minus x of t. Now, Zt of t is written in terms of a dynamic component and pseudodynamic component. If you rearrange these terms, I get this force to be 2z minus x minus y. I can define another quantity g of t, which is 4f divided by k, so that I can focus on the quantity 2z minus x minus y. This is related to the force in the left spring. Suppose now I ask what is the variance of g of t, what is this power spectral density function. We could go ahead and do this analysis. Z is this and Zt of omega will be this, and h naught of omega is the frequency response function which is given by this. Here xt of omega is written, Fourier transform of x double dot is written in terms of Fourier transform of displacement, that is the truncated x of t. That is why we are seeing omega square here. That omega square is pulled out here and I get this. So, SGG of omega, if I use this definition of the power spectral density function, this is given here, and GT of omega is G of t is 2 z of t minus x plus y. So, if I do this, I get this, and SGG of omega can be shown to be given by the auto power spectral density function of the left hand side support excitation multiplied by one transfer function. The auto power spectral density function of the excitation at the right hand side multiplied by another transfer function, and another transfer function H3 of omega, which multiplies the amplitude of the cross power spectral density function between x of t and y of t, x double dot of t and y double dot of t. We can show that this H1, H2, H3 are given by these functions. Here I have introduced a slight variation. I have multiplied this transfer function by a filter h of omega whole square. If you look at the nature of H1 of omega, you see that there is a term 1 by omega to the power of 4, and this will contribute to singularities in the response, which is due to improper specification of the power spectral density functions. To circumvent that, we multiply by a transfer function which actually kills this singularity and leads to meaningful results. It is an artifact. I will explain this function shortly. H3 of H1 and H2, we can show that they are actually positive, although that is not manifested here. I will show it in the next slide that H1 and H2 are strictly positive, whereas H3 depends on this phase spectra, and this could take values which could be either negative or positive. In any case, the variance of the quantity g of t is given by the area under this function. So, again there are 3 transfer functions H1, H2, H3, which multiply respectively the auto PSD of x double dot of t, auto PSD of y double dot of t, and the cross power spectral density, amplitude of cross power spectral density function between x double dot and y double dot. So, to clarify the role played by HF of omega whole square, we can propose a proposed form of this transfer function is given here, and if you actually plot it, that is how this looks like. This blue line is this square of this HF of omega whole square. This function is 0 at omega equal to 0, and this enables us to, when this is multiplied by functions with singularities at omega equal to 0, a few of them can get eliminated. As omega becomes large, of course, this function becomes 1, and therefore, multiplication of this function does not affect the product once we cross the frequency of say 30 radian per second or so. So, the location of this peak can be manipulated by adjusting this filter frequency omega f, and also we can the details of the decay to 1 can be controlled by varying this damping factor zeta. Typically, the plot that I have shown is for the central frequency of the filter is 5.5 radian per second, and damping is fairly high. This is basically an artifact to remove singularity at omega equal to 0 in the response. By rearranging the terms in H1 and H2, we can also show that H1 and H2 have this representation, and if you carefully observe this, you can see that H1 and H2 are non-negative, they are actually positive. So, if you look at this expression for variance, we see that the first 2 terms essentially make positive contribution, and the third term can make either a negative or a positive contribution. So, if we now ask the question, what should be the nature of cross power spectral density function which produces highest or the lowest variance? That will be controlled by this product. Basically, that will be controlled by the nature of this H3 of omega. If Sxy is 0, that is when x of t and y of t are independent, then we get of course the variance to be simply the sum of contribution from first two terms. If it is fully coherent, that means if this is equal to product of Sxx into Syy, I get another value of this. One may be tempted to think that these two represents limiting values of the variance of G, but it turns out that they are not the limiting forms which lead to highest and lowest variance. So, I leave this as an exercise if you for you to determine the nature of this cross power spectral density function which produces the highest variance and the lowest variance. You could assume that phi xy of omega is specified, and a hint to this solution is that the optimal solutions are produced neither by fully coherent nor by incoherent motions. That means there exist special forms of cross power spectral density functions which produce the highest response. So, in case you do not know the properties of cross PSD function and you want to get the worst response, you can use this optimal cross power spectral density functions and get an idea of what could be the highest variance. There is another exercise associated with this problem. We have shown the variance of the response in terms of contributions from auto PSD of x, auto PSD of y and cross PSD of x and y. Another way of looking at this is, if you look at the way we have written the response, we had a pseudostatic component and a dynamic component. Z of t is written as a total response is written as a dynamic component plus pseudostatic component. So, if you look at variance of the total any of the total response quantities, it will be having contribution from variance due to pseudostatic component and variance due to dynamic component and another contribution which comes because of correlation between dynamic and pseudostatic components. So, we can also write the variance of the response. If you have to really rearrange these terms in a slightly different manner, you can show that the variance of the quantity G of t consists of a contribution due to pseudostatic component, a contribution due to dynamic component and a contribution due to correlation between dynamic and pseudostatic component. If you do that, you can show that the pseudostatic component is given by this, the dynamic component by this and the correlation component by this. This I leave it as an exercise. This essentially requires rearrangement of these terms. In problems involving support motions in computational modeling, many finite element softwares do not have capability to apply support displacements. Instead, they convert the problem of a support displacement into an equivalent problem of an external force. How it is done? So, there we use what is known as a large mass concept. The basic issue here is, can we replace a given system with support motions by a modified equivalent system in which support displacements are replaced by external forces. So, to consider that problem, we will consider a simple example, a problem of a differential support motion where one of the support does not actually move, other one moves by x of t, and let us assume that x of t is actually a harmonic displacement. We can easily write the equation for this in terms of the displacement, and I can get the steady state value of zt of t given by h of omega exponential I omega t, and h of omega is this transfer function. You can easily do that because in this is the equilibrium equation, and on the right hand side I have a harmonic driving. In the steady state, the response also would be a harmonic at the driving frequency with an unknown amplitude h of omega. If you substitute this into this equation and rearrange the terms, you can easily derive this. Now, what is done in using large mass concept is, this support is replaced by a huge mass. These are point masses, the size of the rectangle is not so important, but just to pictorially represent this is a large mass, I have shown a larger rectangle here, and the support is replaced by a large mass and the degree of freedom is released, and on this mass we apply a force minus m x double dot of t. What is x of t? X of t is a support displacement here. What I have done? I have removed this support and added a large mass there. On the large mass I am applying the force m x double dot, right, but the support is now removed. So, this is now becomes a 2 degree freedom system. We have not yet encountered multi degree freedom system in this course, but we can proceed a bit. If I write now the equilibrium equation for this system, there will be one equation governing u of t, which is given by this. There is an external force m omega square exponential I omega t, and this mass which where degree of freedom is v of t, I get this. I can put it in the matrix form, and on the right hand side I get a forcing function for this degree of freedom u of t and no forcing function on this. Again, if I now consider steady state response, the system here is again linear, time invariant, driven harmonically, therefore response is also harmonic at the driving frequency, but with certain unknown amplitudes. So, if I now assume in the steady state this u and v is given by some capital U and v exponential I omega t, I do not know what are these u and v. If I substitute this expression into this and solve for this vector u v, I get the expression in this form. This is something that you can easily verify. Now, the claim that is being made here is, as this mass becomes large, the amplitude of response of this mass for this 2 degree freedom system approaches the amplitude of response of this system for large times. That means, what we are assuming, the amplitude of response here is h, whereas amplitude of this mass here is capital V according to this notation. So, the claim is limit capital M tending to infinity V of omega goes to h of omega. This can be verified. I have shown here as an illustration here. The blue line is response of the single degree freedom system in which one of the support is moving harmonically. The other lines are response of the 2 degree freedom system where the left hand support is removed and a mass is inserted there, and that mass carries the force m x double dot. The various colors that you see here are for different values of this m. So, if m is very small, half of the main mass, then the system has 2 degrees of freedom and there will be 2 peaks. But as this capital M becomes larger, what happens is the lower frequency starts moving towards 0th frequency, and in the case where capital M is 10 to the power of 6 times this mass of the main system, you see here this magenta line has a small peak almost at omega equal to 0, and this actually now lies on the blue line, which validates the claim that this claim that as m tends to infinity v of omega is h of omega. So, you could analyze therefore a single degree freedom system under one support motion as by an equivalent, you can study an equivalent problem for 2 degree freedom system where there is no support motion, but there is an external excitation. So, many softwares are geared to handle external excitations than support motions. What happens if the system has now 2 supports and each one receives a differential support displacement? So, I replace this support by one mass, this support by another mass, and on this mass I apply minus m1 x double dot, on this I apply minus m2 y double dot, and if I were to analyze this, as m1 and m2 becomes large, these two becomes large, the response of this mass becomes the response of this mass. But here you should see that this has a rigid body motion possible, because omega equal to 0 would be one of the natural frequencies here, and consequently you can also show that the contribution from that rigid body mode in this problem would be actually the pseudostatic response for this system, and the contribution from elastic mode will be the dynamic component of the response here. So, this is one useful trick that is done if you are modeling vibration of large systems in using say finite element methods. So far we have been talking about response covariance, power spectral density, mean, variance, so on and so forth. How about the probability density function of the response? That question we have not yet addressed. We will start with the issue of a case of f of t being a 0 mean Gaussian random process. The output process, that is the response process, is given by this Duhamel integral, and this is a linear transformation on the input process. But this is an integral, this is a differential equation, right. This is a second order differential equation here, this is an integral, convolution integral here. How do you prove that if f of t is Gaussian, x of t is also Gaussian? Okay, that is what we are going to use. A simple intuitive proof for that is you replace this integral by a summation, and we see here that x of t is obtained by a linear superposition of different Gaussian random variables. F of tau for tau n for different values of n actually Gaussian random variables, and you are adding them linearly. So, a linear transformation of this kind on Gaussian random variables, we have already seen that it retains Gaussian property. So, based on this argument, we can conclude that x of t is a Gaussian random process. But a more rigorous proof of this can be obtained by considering the characteristic functional of f of t and study what are known as its cumulants. I leave that as an exercise, but for purpose of preliminary understanding, this argument should suffice. Another a small exercise in the same in this context would be if you consider now the derivative dx by dt. We have already defined the derivative of a random process in the mean square sense. That is given here. If this limit is interpreted as limit in mean square sense, this will be the mean square derivative of random process x of t. Now, let x of t be a 0 mean Gaussian random process, and suppose if I define y as x2 minus x1, where x2 is x of t plus h by h and x1 is x of t by h, where h is we are not still imposing the limit h going to 0, h is some finite non-zero quantity. We can easily show that y is Gaussian, and we can write the probability density function of y. Now, the exercise I want you to tackle is you have to examine the limit of this probability density function as h goes to 0. The limiting operation here is on density function. It is quite different from mean square, the definition of limits in mean square sense. So, the discussion of this should be with reference to the two different modes of convergence that we are using. If we now consider the PDF of the response process, we have now taken that x of t is also a Gaussian random process. What it means? The first order density function is given by this. A second order density function, I am now not writing the expression, but I am notionally representing as normal random variable with 0 mean and covariance given by this. If you consider n time instants, this will be a n-fold n dimensional Gaussian random variable, the mean continues to be 0, R is n by n covariance matrix. Now, typically we are interested in answering the question, what is the probability that the response stays below a safe limit alpha for a time duration 0 to t. When we say x of t is completely specified, when I know its nth order probability density function, will such complete description of x of t would enable you to answer this question or determine this probability? I am not sure. Why? Suppose if you select t1, t2, t3, tn which all belong to 0 to t such that ti is I delta t and n delta t is t. Now, can we approximate this, can we find this probability by approximating by this integral? That means, a n-fold integration on nth order density function, where domain of integration is the intersection of all these x's being less than or equal to alpha. So, it is a n-fold integration. Even if you are able to evaluate this, I do not think we will be able to approximate this. I mean, this would serve as an approximation to this, because this integral will be equal to this provided this n goes to infinity. As n goes to infinity, the dimension of the integral is becoming increasingly large. That means, it appears as though that the answer to the question we posed is yes, maybe yes, as n tends to infinity. Even if this were to be acceptable, we still need to evaluate a multifold integral with dimension n and that n set to become very large. I think this is by no means is a simple task. So, we reach a seem to reach a dead end here, where we seem to have managed a complete description of x of t, but still we are unable to answer a very important question on whether the response stays below a critical value over a given duration. So, this points towards the fact that we need different kinds of descriptions of x of t. A joint density function of any order still does not seem to be adequate. So, we will address these questions in the next coming lectures. So, we conclude this lecture here.